then does it mean that the non-smoker has twice probability than probability of surviving or living more, okay, living a given number of years, given number of years as does smoker of the same age. In other words, imagine this guy is smoker and has a 25 years age, and this guy has is non-smoker and 25 years age. Is the probability of non-smoker having a longer life or surviving for say some number of years, say for example 10 years or next 50 years, whatever, is double than the probability of the smoker who is at the same age as this guy actually? Let's try to analyze this problem actually. The answer is really no, it's not double, it's really square actually. The probability of survival of this is a square of the probability of survival of this actually. So it's not double, it's more actually. Okay. So how can we answer this interesting question? So here's a one possible way to approach this problem. So say imagine lambda s of t is the hazard rate function or failure function. So it's failure rate function for smoker, and lambda n of t is a failure rate function for non-smoker. Okay, so it's a failure rate function for non-smoker actually. So according to this myth, the non-smoker, so if you assume this myth is true, the non-smoker survives double than the smoker actually. So in other words, I can say that the non-smoker the lambda n of t is the twice of lambda s of t. But does it mean that probability of survival of non-smoker is also double than the probability of survival of the smoker actually? Okay, if the both age same now. So let's try to analyze that actually. Okay. Now let's talk about the probability that an A years old, okay, A years old non-smoker non-smoker will survive until an age until age say B, where A is some age before B. So, so A is say for example 25 years and B is say 60 years or something like that. Okay. So let's compute this probability. So probability that A years old non-smoker reaches age B should be what? Let's think about that. So it should be same as saying that probability the non-smoker lifetime is bigger than B, given that non-smokers lifetime is bigger than A. In other words, it has survived A because if this guy is A years, non-smoker guy is A years old, okay, and I'm interested in the probability that it will survive up to B, then this probability is basically can be written as this conditional probability that imagine a non-smoker lifetime has survived, more than A is more than A. What is the probability that non-smoker, given that the non-smoker's lifetime is bigger than A, what is the probability that non-smoker lifetime is also going to be bigger than B actually? So it will survive until the age B. So let's compute this probability. So we can compute this probability by saying what? So for example, if I call this event as say B and I call this event as A, then this would be same as probability of B intersection A divided by the probability of A. Now, which of the event is bigger? Is this event bigger, that the lifetime of an object is of non-smoker has survived till A, and the non-smoker and the non-smoker has survived till B. Okay, so the life of the non-smoker is going to be bigger than A. So I have this. So this is going to be this. So if A has survived A years, then where does this guy can die? So it can die at any instant actually after the A. And what is the what do you call the event that non-smoker will has survived up to the age A, and it will die say at any instant, what do you call, after B. So which set is bigger? Is this set bigger or this set bigger actually? So you can see that this set is a bigger set actually, and this is a subset of this. No, this is a subset of this. So what would be the intersection of both? So it's going to be the probability of this. Okay. So in other words, I can say this is same as probability of B by the way, you can give some other names. Let's not give, say for example, B and A are reserved. Okay. So let's just write it as it is actually. Okay, this is same as the probability that the non-smoker life is bigger than B divided by the probability that non-smokers life is bigger than A. Okay? So there was also an intersection here, but since this set is a subset of this, so that intersection becomes the smallest set actually. Now this probability, okay, so if I call this random variable as say x, then I can write this as probability of x bigger than b. But this probability can also be written in the terms of the CDF. I can say that this is same as 1 minus, okay, 1 minus CDF of the non-smoker evaluated at B divided by 1 minus CDF of the non-smoker divided by A actually. Okay. So this is what is going to be the probability that A years old smoker will survive till age B. Okay. Now, using the relationship between the CDF and the, say for example, the failure rate. So we know that failure rate can be determined as 1 minus exponential of the integral from 0 to t and lambda of t dt. Okay, so using this, I can rewrite this expression as, so I can take this on this side and I can take this on the other side. So it's going to be, was that the case? Yes, this was the case actually. So the 1 minus this is going to be equal to the exponential of this actually. So I can write this as an exponential of the integral that it has survived till b. This is the smoker dt divided by the exponential of the integral from 0 to a of lambda s of t, what we call dt. Non-smoker, sorry. Non-smoker. Because we're going to use the failure rate of what do you call the non-smoker. I can put these integrals on both sides. I can put them in a single expression actually. So if you're going to put this, the both into the single expression, you're going to get this, that this is equal to the exponential of, what do you call, the integral from 0 to a of lambda n of t dt minus integral from 0 to b, okay, of lambda n of t dt. Okay. So the one integral is from 0 to a and the other integral is from say 0 to, what do you call, b, and from 0 to a you are subtracting integral of 0 to b, so what is going to remain is going to remain the integral from a to b. There is a minus as well here. I can put a minus here and I can put a plus here actually. Yes. Okay? So what is going to remain? It is going to remain as the exponential of the integral minus that goes from a to b of lambda n of t dt. So this is really what is called the probability. So this expression is really the probability that an A years old non-smoker will reach to the age B actually. So I can write this probability in the terms of the survival function. I can express it in the terms of the survival function. So what can I do? I can repeat the same analysis, precisely the same steps for smoker actually. So I can say the probability that an years old smoker, okay, smoker will reach age B is going to be equal to what? Everything is going to be same except exponential of integral from minus a to b, and it's going to be lambda s of t and dt. This is what it is going to be. Okay? Okay. So what should I do now? By the way, this failure rate are, you should write it correctly. Okay, so there's one little correction. This failure rate, lambda of t, can be interpreted as the death rate of smoker, non-smoker, and this is the death rate of smoker actually. So in principle, non-smoker's death rate is not double of smoker's rate, but it should be other way around actually. That smoker's death rate is double of the non-smoker's death rate actually. Okay, so it is more fast, more rapid actually. Okay, so that's a correction we should do. So what I want to do, I want to substitute the value of lambda s here, so I'm going to get exponential of negative of 2 from a to b and lambda n of t dt. Okay? And if I have this 2, so I can write this as exponential of integral, negative of integral from a to b, lambda n of t dt, and the square actually. So I can write all of this as the square of this. Okay? Because the powers multiply. The powers multiply. So you're going to have this. But this is what? This is precisely equal to the probability that a years old will survive until the age b actually. So in other words, I can say this is same as that the probability that a years old non-smoker, okay, survives till b. I'll write it a bit more explicitly, that this guy is equal to the probability that a years old non-smoker, I'm not writing smoker, non-smoker, survives till age b. So if you see, because this guy is equal to this, so the probability of smoker survives, a years old smoker survives or reaches to the age b is the square of the probability of non-smoker actually. Now the probabilities are numbers between 0 and 1. So if you square them, they become smaller actually. If they become smaller, they don't become what do you call double, okay? They become smaller actually. So this guy is bigger, and this guy being smaller of the probability of non-smoker is smaller actually, okay? So the probability of smoker surviving to the age B is smaller than the probability of non-smoker surviving to the age A actually, age B. Okay, because this probability is the square of this probability. Okay, and hence this becomes a smaller number. Okay, so let's for example put this into a numerical number equation. Okay. So let's assume that the death rate of the non-smoker is 1/30, where the t is between 50 to 60. Okay. So the death rate of obviously smoker is going to be 1/15 between 50 to 60. So what is the meaning of this statement? The meaning of this statement, you can interpret it as that the death rate of non-smoker, so the non-smokers dies in the age 50 to 60 on average 1 out of 30 actually. So if you have 30 people, okay, between the age 50 and 60 and they are non-smokers, so the one of them is going to die on average. Okay, 1 out of every 30 will die. While for the smoker's case, if the smoker is ages between 50 to 60, will die, say 1 out of 15, 1 out of 50. Okay, so it's huge actually, it's bigger. Then what is the probability? I guess if I want to compute the probability. So what is the probability that a 50 years old non-smoker okay, will survive or reach to age 60 is going to be equal to what? So for that, I can apply, for example, this formula. So I can say I can have an exponential between say 50 to 60, and lambda n of t is 1/30, and dt, so this would be equal to, what do you call, e to the minus 1/3, which is a number, say 0.7165. So there is 72% roughly chance that a 50 years old non-smoker will survive and reach to the age 60. And what would be the probability of a 50 years old smoker will reach, say, to age 60? So this is really equal to non-smoker age square actually, in other words 0.7165 square. And if you square this number, this is going to be equal to 0.513. Okay, so this is going to be equal to 0.513. So there is around a 50% chance that it will survive while a non-smoker surviving till 60 is, say, 71% chance. So what does this show? Stay away from smoking. Okay, so that's one of the interesting simple application of what we call survival rate function. Now, if you go through the book, then there are gamma distribution and Weibull distribution, Cauchy distribution, and beta distribution. I'm leaving these distributions for you to study for yourself actually. So I can't get into obviously every single distribution. You have to study these rest of distribution yourself. Okay. All of them are interesting. All of them capture a lot of very interesting natural phenomena. They model a lot of natural phenomena. So read them actually. So don't miss them. Okay. So I would like to move to the last part of the lecture. The last part of lecture is that if you have a distribution function of a random variable, then how you can find the distribution function of a function of a random variable actually. Okay. Go to the next thing. That if so the next thing is this. If x is a random variable and I know that its distribution function is say fx and its PDF is small fx, and I have a function say g of x actually. Okay? Random variable y, that is g of x. The question is, for this y, what is the CDF and what is the PDF actually? So in other words, if I know things about g, can I find what do you call the distribution function of the function of a random variable actually? I mean, if you remember, we did a neat trick. Okay, that trick works, say for example, in many situations. So if you have a simple function, say imagine I have a random variable x whose distribution function is fx and PDF is small fx, and I have a random variable y that is equal to x power n, and I want to know that okay, what is the CDF of this y, which is a function of a random variable, and the PDF of this y. Okay. So the trick that we have done previously as well, that if you want to compute fy of x, then this is same as computing the probability of y less than or equal to x, but this is same as computing the probability of x power n less than or equal to x, and this is same as computing the probability of say x being less than or equal to nth root of x actually, and hence this is this fy of x is going to be equal to fx of x, fx evaluated at x power 1 over n. In other words, the CDF of y can be written as in the terms of the CDF of x evaluated at x power 1 over n. And if you want to find the PDF, you need to differentiate both sides. So the fy of x is going to be fx evaluated at x power 1 over n, and obviously multiplied by x power 1 over n, derivative of the x power 1 over n, which is going to be 1 over n times x power 1 over n minus 1, which is going to be 1 minus n by n. So this is what is going to be really the CDF of it actually. Okay. Obviously, since all these are probabilities, so the x should be between 0 and 1. Okay, it can't be something bigger than 0 and 1 actually, because otherwise this number can grow exponentially, or it can be bigger than 1 actually. Okay. Say for y equal to x square, you can have a trick actually. Fy of x, say this is same as probability that x square is less than or equal to x, but I can write also this as probability of x squared less than or equal to x, and hence I can say this is same as probability of absolute of x less than or equal to x. But this is same as probability of x being not x but square root of x being between square root of minus x and between square root of x. And this probability can be computed as fx evaluated at square root of x minus fx evaluated at square root of